In this video, I'm going to talk about the characteristics of alpha, beta, and gamma radiation. It's part of topic 7 in IB physics. It's in the SL section. Take a moment and read the success criteria that we're going to try and cover in this video. Okay, so let's start with alpha particles. They are the heaviest. They're alpha because, well, basically they didn't know what it was, and let's start with the Greek alphabet. First letters are alpha, beta, gamma. Now, this font isn't the greatest to read, but that is alpha like this. I refer to it as the fish swimming. So I've got an example here, and it's kind of good to have an example that you recognize so that you could use it in answering a question if you needed some kind of reference to. But in the IB, you don't have to memorize these things. In previous versions of the data booklet, we used to have a periodic table, and it's not there anymore. So therefore, they have to give you some information to figure out which elements we're dealing with. So please look out for the information given there. It has to be there. Okay, so alpha particles, the heaviest ones I said, it's made up of 2 neutrons, 2 protons. That means it has an overall charge of +2. It definitely has a mass. It's the heaviest of all of them, and it doesn't move as fast. It's definitely the slowest. Probably as well, if you think about it, it has the most mass. Now, it doesn't penetrate very far, again, due to its mass. It could be stopped just by paper. So no, it's not going to go all the way through my body. In fact, it wouldn't even get past my skin. It does, however, ionize. And for those of you who don't take chemistry, ionize means to make an ion, to make a charged particle. Now, there's no way it's going to knock something out of a nucleus. So how does it ionize? How does it make a charge? It must hit an electron and knock it away from the atom to make it a charged particle. That means it always makes positive charged particles because they have one less electron. Now, if you take a look, just a reminder about balancing nuclear equations. This is not like chemistry because that's all about gaining or losing electrons. We have changes in the nucleus. So at the first we have here, we have 92 protons in uranium. Now, that's our beginning. After the reaction, now remember, this cannot be a equal sign. There's no way thorium and the alpha particle are going to come together to make uranium-238. It goes in one direction only. Okay, so in our products on the right side, we have for sure 2 here because we know an alpha particle was given off and it has 2 protons. So I always panic if things aren't, balanced and conserved. That means there must have been 90 protons here in this element. And it's the number of protons that determine the element. 90 protons make it thorium. And similarly, with the nucleon number, 238 is what we begin with. And afterwards, we know for sure we have 4 here because it's 2 protons, 2 neutrons. And that means there must be 234 left over for this particular isotope. Okay, so next in the alphabet, beta. So let's talk about beta particles. I've got an example here, carbon-14. It's the isotope used in radioactive carbon dating. And we have it so you can see here is my beta, sometimes written like this, sometimes written like this, because it is a high energy electron that's been released from the nucleus. Now, normally down here I should have the number of protons, and I don't have a proton now, but I have an electron. So we're going to put a -1 there instead of a +1. So let's look at balancing this nuclear reaction. I had 6 protons. Now I have a -1. So that means the remaining nuclei will end up having 7. If you take a look, I used to have 6 protons, 8 neutrons. Now I have 7 protons and 7 neutrons. A neutron has turned into a proton, kicked out an electron at the same time. Charge is still conserved. Remember, we have an arrow, not an equal sign. So when that beta particle is kicked out, what kind of characteristics does it have? Well, it's going to have a charge of -1. It has a lot of energy and a very small mass, which means it's going to be traveling pretty close to the speed of light, but not quite because it does have a mass. Now, because of its smaller mass and higher speed, it's not stopped by paper. It can actually go through it. But if I had a piece of aluminum about 3 millimeters thick, then it would be stopped. So in terms of my skin, I said with the alpha particle, it wouldn't penetrate my skin, but the beta particles would penetrate somewhat. Now let's think about the ionization again. It's a high energy electron. So if it hit an electron, again, something with the same mass of it, it probably would be able to kick it out, but it's not going to be as good as the heavy alpha particle hitting the electron. Oh, but wait. What I just told you was all you ever needed to know if you were just doing IGCSE or some other grade 10 course. If you're doing IB, you can't stop there. Because what they've found is that these beta particles didn't always have the same amount of energy coming off. And panic sets in and says, what do you mean energy's not conserved? Physicists would, oh my goodness, oh my goodness. So Fermi came up with this idea that there had to be another particle to be able to take some of that energy. Being Italian, and the idea of something really, really small because we don't think it has any mass or next to no mass, he called it a neutrino, a baby neutrino. All right, well, you don't need to know this exact curve, but you do need to know the reason why we have to include a third particle. And if that wasn't enough, we also need to realize that that electron could also have been a positron. So I've got a few things I want to add in here. So I've written up here again the previous equation with carbon turning into nitrogen. Now I have here a neutrino. Well, actually, I have an antineutrino. And when you do topic 7.3 in the IB syllabus, you're going to talk about conserving the lepton number. And for that reason, this must be a antineutrino. So let's take a look what I have down here in my second equation. I have magnesium 23, creating 23 sodium, my positron, and now I'm going to have a neutrino, not an antineutrino. These must be written in for the IB syllabus. So I should, if I want to put the whole nuclide notation, at the bottom now I need to have a 1 because I do have 1 as a positive charge. It's not a proton, but it does have a positive 1 charge. Okay, and finally gamma rays. Now, gamma rays typically are given off after another type of radiation. Just like you've talked about electrons going from lower energy levels to higher energy levels when they gain energy, and when they have too much energy in that excited state, they release a photon to come back down to the ground state. The nucleus can do something very similar. So if it gave off an alpha particle or a beta particle and it has too much energy still, the nucleus then can give off a photon. In this case, there's so much energy, it's a gamma ray, to go back down to the ground state. So a lot of the times we will write a little star here to signify that this barium nucleus is in the excited state. Now that gamma ray is the same kind of gamma ray that we've talked in any other part. It is an electromagnetic wave, but it has a lot of energy. It doesn't have a charge, and we're going to talk about electric fields and magnetic fields in just a moment. Electromagnetic waves have no mass. It obviously will travel at the speed of light then. And for all of these reasons, it takes a lot to stop it. It also doesn't really ionize well. So hopefully this has given you a quick review of alpha, beta, and gamma radiation, as well as writing some nuclide notation and balancing nuclear equations. Don't forget, for beta particles, we must include the neutrino or the antineutrino. I hope this helps.